Okay, so pretty good. So we are done with chapters 1, 2, and 3, most of which is mainly review. Today we are going to start with chapter number 4. Okay, and then one thing I want you to pay attention to is that the midterm is coming up on the 8th. Okay, midterm is coming up on the 8th, and that's during the class time. And what you would have to do is to log in using a webcam. Okay, I'll let you know more about it. If not everybody might have access to webcam, so on and so forth. So I'll let you know what to do if you're not able to attend the exam using a webcam. Okay, so on and so forth. So the idea is that we are making good progress, keeping to schedule pretty much. Okay, so quickly reviewing what we did in the last class is the idea of series and parallel resistances, which is pretty straightforward topic. You should be very familiar with this from your earlier courses. Okay, so in series, the resistances add. So R equivalent, resistances in series and resistances in parallel. This is what we did in the last class. Okay, in series, equivalent resistance is equals to the sum of all the resistances. Okay, if there are n resistances, then the equivalent resistance is equals to the sum of all the resistances. Similarly, in parallel, the 1 over the reciprocal of equivalent resistance is equals to the um, sum of one of the reciprocals of the resistance. Okay, so in parallel, we have the idea that the reciprocal of equivalent of a bunch of resistances in parallel is equals to the sum of the reciprocal of all the resistances. Okay, a quick sanity check is that in parallel, the equivalent resistance is always smaller than the smallest single resistor. Okay, so that's the idea. This is something we looked at in the class so far. Then we moved on to talking about voltage divider and current divider circuits. Okay, so the idea was that voltage divides between resistors in series. The voltage is exactly the same when they're connected in parallel. When I have a current divides between resistors in parallel, and then the ratio of the current division is the inverse of the resistor values. Okay, we understood this in terms of traffic flow. If I have a total number of cars entering a road, the road with many obstacles, many stop signs, many stoplights, many signals and speed bumps that experiences lower traffic, and the other with very little resistance. The HOV lane has a bit more traffic. Okay, so that's the idea. This is what we discussed in the last class so far. Okay, so let's continue from there. I mentioned that this course is all about giving you techniques, different techniques for circuit analysis. Okay, so we are going to look at more techniques in this class today. Okay, so importantly, node voltage method, mesh current method, so on and so forth, source transformations, Norton and Thevenin equivalent. Okay, let me see if I have a there. Okay, the topics that we are going to talk about today in this chapter are node voltage method, okay, a mesh current method. Okay, these are different techniques to analyze and solve for circuits. Then look at source transformations, including Thevenin equivalent and Norton equivalent. Okay, so far We looked at different kinds of KVL, KCL, other introductory techniques, right? Series and parallel combination, the different kinds of techniques um, to solve for different circuits. Okay, so we are going to extend our repertoire of our tool set. Okay, beginning with node voltage method. So before we do that, I want to spend a little bit of time talking about using MATLAB in Engineering 17. Okay, MATLAB is a very handy tool. Among a lot of other things, it can help us even um, speed up analysis of linear equations. So far, what we have done was we developed a set of equations. Okay, let's say there were three unknowns. Then we developed three equations, linear equations, using KCL and KVL, different nodes, different loops, so on and so forth. Then we solved them, right? This was the idea that we followed so far. But as we will see, as the circuits become more and more complicated, more and more involved, we'll have to see, we'll have to have a calculator, a handy tool. MATLAB can be one to help us solve a system of linear equations. So equation 1, equation 2, and equation 3, and solve them simultaneously. We did that manually so far. Okay, now the idea is to use a MATLAB tool. So it's quite common that analysis creates a set of linear equations. Okay, it is not very common. The solution to that set of linear equations is the independent variable sort for the analysis. So MATLAB is a very useful tool to help us in this process. Okay, so I'm going to give you some information on how to access MATLAB. There are two things you can do. You can download MATLAB for free, which I strongly recommend, okay? Because it is available to Sac State students for free, students and faculty. It's a very handy tool. If you do not already use it, I strongly recommend that you download it and use it. It has many, many wonderful features built into it, tool sets, toolboxes, so on and so forth. The other option is, if you're averse to downloading MATLAB by yourself immediately, I would still encourage you to download it sooner than later, at a later time. I urge you to consider that strongly. Another option is to use it. Some of our servers, Hydra especially, has installed version of MATLAB. So you can simply remote desktop into Hydra and then use it. So in order to be able to do that, so remote desktop into Hydra. Okay, so the prerequisite is that you use a global protect VPN. Okay, you use a global protect VPN, so you have to download this software before you can actually remote desktop into Hydra. Okay, so you need both of these, all of these softwares, they're available on SACState. All you have to do is Google SACState Global Protect. So when you Google this, it's going to take you to a download website where you can download this. The same for MATLAB as well. SACState download MATLAB. It will take you to a website where you can download that software. Okay, so all the other information, step-by-step information on how to access once you start remote desktop. Okay, once you remote desktop, how do you start? Okay, a pictorial and verbal step-by-step procedure is shown here. Okay, as you can see, a bunch of software is installed and MATLAB is right there for us. And this is on remote desktop. This is Hydra. Once you log into Hydra, you're able to access MATLAB. The other option, obviously, is to download. So there is more information on how to get started with MATLAB, the open screen, so on and so forth, where you type commands, where you type your new program, so on and so forth. Okay, so as it turns out, MATLAB is just one tool. There is a bunch of tools out there. Okay, but then MATLAB is a very popular tool. You'll be in good shape. Um, you your um, prospective employers will find it a good skill set if you display that on your resume. Okay, now there's a very quick way to do MATLAB. There's a very simple code. Okay, all the code that you have to write for MATLAB is just about 3 lines of code. Okay, let's say you want to solve a set of linear equations that looks like this. Okay, two equations, 1, 2. There are two unknowns. You're trying to find the value of V1. You're trying to find the value of V2. And that takes the form of two equations. Okay, so what you have done is you have to express this equation 1 and equation 2, combined, you have to represent it as a matrix. Okay, if you think about it, this matrix, this number 29, corresponds to the coefficient of 29 over here. Okay, this guy, -1, corresponds to a negative V2 coefficient over there. Okay, similarly, so this matrix is representative of the coefficients that you find for your variables. Okay, similarly, this 17 is, let's see, I don't know, this 17 is representative of the coefficient for V2. So you can see the relationship between the variables, the equation that you have, and the matrix that you want to um, enter into MATLAB. Okay, then there is, of course, the um, variables themselves, V1 and V2. Okay, these are the unknowns. Now, the other stuff is straightforward. The constants are shown in this 2 by 1 matrix here. So as you can see, all you have to do, it's a very straightforward process, is to create a matrix A which has two rows. The first row is 29, -1. The second row, which is entered into MATLAB using the semicolon, is -1 and 17. Okay, so that's all there is to entering your matrix A. Okay, then you enter the matrix C, which is the coefficients, which is the um, constants over here, 2880 and 270. Sure enough, you plug those in. Now, how do you calculate the unknowns? You're trying to calculate the value of this guy. That's your B. This is your A. And this is your um, constants, C. Now, B is simply C over A. Okay? Or all you have to do is inverse of A times C. So very straightforward, simple 3 lines of code is all you need to solve a system of linear equations. Okay, and you can extend this to more than two equations. If you have three variables, three equations, that's as easy as just 3 lines of code. 10 unknowns and 10 equations. Well, it's much easier with MATLAB than having to do that manually. Okay, questions, please. Okay, so I strongly recommend that you try your hand with MATLAB. Okay, and then it'll throw out numbers. It'll give you solutions for, you can even do matrix. You can even do complex numbers. Okay, you can even do complex numbers, not just real numbers. Okay, so a very useful set of tools. I strongly encourage you to start using MATLAB. And the sweet part is you can use it even on exam. Okay, on the exam, and by the way, this is an important thing that you want to remember. On the exam, you may encounter a set of 3 equations or 4 equations and 4 unknowns that you have to solve simultaneously. And why not use MATLAB when we can use it on the exam as well? Okay, so that's the idea of using MATLAB to solve a system of linear equations. So let's continue with this. So I promise there are 4 techniques that we are going to look at: the node voltage method, the mesh current method, source transformations, including Thevenin's and Norton's equivalent. Okay, so what questions do I have so far? Okay, just give me a second while I browse to my notes here.
Will notes be allowed on the exam, or is it all just closed note, closed book?
You're free to use notes. You're free to use notes. So I don't care if you have an open book, closed note. So any tool that you can bring to bear to the exam and use it to your advantage, I'm fine with it.
All righty, thank you.
Yep. Other questions, please.
So the first exam is the first 3 chapters, right? So chapter 4, is this going to be on the test number 2?
Chapter 4 is going to be on test number 2, exam 2, correct?
Okay, thank you.
Yeah. It's a good question. All right, so let's see. Chapter 4, circuit analysis. All right, so let's begin with the node voltage method. So before we do that, let's define a few terms here. Node, as you're already familiar with, is a point where circuit elements join. Okay, when there is more than 1 connections. Okay, all of this is 1 connection. Okay, and there is another wire joining from up top, from north south. Okay, then that point is where node, that's what we call a node. Okay, node definition is used to write current equations. As you have seen, we often associate a voltage at a node. Okay, and the sum of currents, sum of all currents, Ix, x is 1 to n, all the currents at a node is 0. Okay, so this is the fundamental premise of KCL. Kirchhoff's current law states that the sum of all the currents at a particular node is 0. Okay, then we define a reference node. That is a node which is assumed to be, let me say that, which is assumed to be at the lowest potential. Okay, so we begin by defining a reference node from here on out. Okay, now we are already familiar with the idea of a loop, right? Loop is a path through the circuit that begins and ends at the same node. We defined a bunch of loops in the last class, in the previous classes. Okay. Now a subset of loop is a mesh. Sorry. Okay. A loop that does not contain any other loops, that is called a mesh. Okay. So earlier we used nodes and associate voltage with them. Okay. So this is step one. And then KCL was associated with a node. KCL states that the sum of all the currents is 0. Now, when it comes to mesh, we associate mesh current. Okay. On the other hand, KVL states that the sum of voltage drop across a loop, all voltage drop across a loop is 0. So KVL, earlier we saw loop voltage. Here on out, we are going to see loop or mesh currents. Okay, slightly different. Earlier, we saw currents at a node, which all summed to 0. Now we are going to associate voltages. So slightly different from what we have done before. Okay. So node voltage and mesh current. Okay, node voltage and mesh currents. So this is something that we looked at so far. How many equations do we need to set up to solve a circuit? Well, that's equal to the number of circuit unknowns. Okay, number of independent circuit unknowns. Okay. And then of course, we use simulation tools a lot of times. When we want to do our hand calculations, we use MATLAB. So let's have at it. Let's start with the node voltage method. Okay, node voltage method of solving for different unknowns in a given circuit. Okay, here is the general procedure. Okay, the idea is using nodes, we set up sufficient number of independent equations in order to solve for all unknown circuit variables. Okay, so we write equations usually in terms of voltage and other circuit element values like resistances. Okay, and then we apply eventually KCL. So when we do node voltage method, the underlying phenomenon, the underlying theory that we use is that of KCL. Okay, so the very first step to do is to pick a reference node. Okay, from which we calculate voltage changes, voltage drops. Okay, so it's better shown using an example than talking on and on. So let's start by taking this example. Okay, let's solve for the voltages and currents in this problem. So let me start by taking a screenshot. Okay. Okay. Copy that. Let's see, add a page. So here is my circuit that I'm trying to solve using node voltage method. Okay, node voltage method solution. The very first thing I do, step number 1, is to identify a reference node, ground node. Okay, so and I'm going to annotate this guy right here as the ground node. So that is step 1. Okay, then I'm going to, that's step 1. Step 2 is identify certain nodes. So let's look at some nodes here. So I'm going to call this one and this one as nodes. Okay, so let me do that. So this is node 1 and this is node 2. Okay, so this is node 2. Now, let's see. That's node 1 and that's node 2. So now I'm going to define voltages V1. Okay, that corresponds to the um, node voltage. So the voltage at node 1 is V1. Okay, so positive and negative with respect to ground, and the voltage at node 2 is V2. Okay, so this guy is V2 plus and minus. Okay, that's step number 2, is to identify nodes and then set up node voltages. Okay, now you can see, it's easy to see the beginnings of why we like to call this a node voltage method. Okay, so the next step, that's a little bit unsettling in the sense that I'm going to begin by identifying currents. Okay, I'm going to begin by at each node. So the idea is at each node, look at all the currents that are leaving that node. Okay, here is the idea of KCL. Okay, so I'm going to, at each node, I'm going to sum all the currents that are leaving that node. So if you think about it, at node 1, there are 3 currents that are leaving. Okay, there's one current that is going left in the 1 ohm resistance. There is a current going right in the 2 ohm resistance, and there's a current going down in the 5 ohm resistance. So once I apply KCL at node 1, what I'm going to end up with is V1 minus 10 volts by 1 ohm. That's the current in the 1 ohm resistance. So there is a voltage of V1 and there's a voltage of 10 over here. So the voltage drop across this resistance is V1 minus 10, Ohm's law. Okay, V1 minus 10 over 1 ohm plus, let's look at the current going right in the 2 ohm resistance. So that is V1 minus V2 over 2 ohms plus, let's look at the current going down in the 5 ohm resistance. So which is V1 minus ground, because I annotated that node to be 0, over 5 ohms. So all of this is equals to 0.
Professor, can I ask you one question?
Yes.
Can't you argue that you could put actually a third node by where 10V and 1 resistance is right there in the corner?
Right
and
here?
Then, yeah.
And another one here?
No, not there, because there's no resistance that basically and have a node for that spot.
Okay.
And then you could apply a super node on the 10 on that node on the corner, because the reference node is the bottom, thus making the can't you apply it there a super node in that aspect?
That's a very good question. When I have to decide between if there's a node or not, the question I ask myself is, well, look at this current that is coming in here. Okay, let me show that. This current, okay?
Yes.
Is that branching somewhere or is that going right into this? If it has two paths to go, then I would call it a node. If all the current that is coming in has nowhere else to go but through this, then I'm not inclined to calling this a node for this analysis. Does that make sense?
Okay, so it wouldn't really be a node there in that corner.
Because there's no, it's this current is not branching into two different paths, right?
Okay.
There's only really one way for this current to go. For my analysis, the question I'm asking is, if the current has only one path to follow, then I'm not going to consider that as a node.
Okay,
Even if I
perfect.
did, it's not a big deal. Even if I did, all I'm going to get is, let me call this I total. I'll call this I1. According to KCL, I'll end up with I total equals to I1. Okay, it's a trivial equation.
Okay, perfect. Thank you.
Yeah, that's a good question. Thank you. Okay. Now, so that's KCL at node 1. So this is, let me write it out. KCL at node 1. Let me do the exact same thing at node 2 as well. KCL at node 2. And pay attention, here is where it gets a little unsettling. By node 2, I meant this node, right? So what I'm going to do is I'm going to look at all the currents leaving the node. I'm going to add all the currents leaving the node and say that it is 0. So far, we are used to doing things differently. We are used to setting up currents and voltage directions ahead of time. But now I'm not going to do that. I'm going to apply KCL by looking at all the currents leaving the node. Okay, so let's start by looking at this. The current going to the left of this node. Okay, the current going to the left of this node will be V2, which is this voltage V2. Okay, V2 V2 minus V1. So that's the voltage drop across this resistance over 2 ohms. So that's the current going in the left resistance. Okay, so let me do that. So current going left in the 2 ohm resistance is V2 minus V1 over 2 ohms. That's the current going in the left. There's a current going to the right, which is exactly the opposite of 2 amperes. I know I have 2 amperes coming in this direction. So if I have to represent it as current flowing in the opposite direction, then I include a negative 2. Then I want to look at the current flowing down. Okay, so it will be V2 minus ground by 10 ohms. So according to KCL, the sum of all the currents leaving this node is 0. Now I have two equations, equation 1 and equation 2. So I can rearrange this a little bit and do algebraic manipulation. Maybe I'll do just one solution, one problem to manually show you how it is done, and then let you do the rest of the stuff. Okay, so I'm going to copy these over. Okay, so these are two equations I have that came from node 1 and node 2. Okay, now it's just a matter of massaging these equations, algebraically manipulating them to arrive at the answer. So from the first equation, I'm going to factor out V1. So I'm left with 1 by 1 ohm plus there is a 1 over 2 ohm factor over there. So there is a 1 over 2 ohms. And then there is a 1 over 5 ohm factor over there. Okay, so there is 1 over 5 ohms. So that's about V1. Okay, then I look at V2. V2 has a 1 over 2 factor over there. So negative V2 over 2 ohms. Okay, then I can take this guy, I can take this guy over to the other side. I'm left with 10 volts. Okay, so this is equation 1. This is just a manipulation of equation 1. And I can do the exact same thing for equation 2 as well. So V1, when I factor out V1, I'm going to be left with negative half. Okay, and then when I factor out V2 from this equation, I'm going to be left with, I don't know, let's see, V2 over half plus V2 over 1 over 10. So when I factor out V2, I have 1 over 2 plus 1 over 10 ohms in here. Okay, and then there is a negative 2 factor, this guy, negative 2 amperes, which I'm going to take to the other side, 2 amperes. Okay, they should really have been 10 amperes. Okay, so this is the second equation. Now, I massage these equations and bring them into a form viable for my MATLAB. Okay, minus 5V1 plus 6V2 equals to 20 volts. So I have two equations here, equation 1 and another equation, equation 2. So it's easy for me to plug them into MATLAB. Okay, I'm going to write A to be equals to 17, negative 5, negative 5, and 6. Okay, and then I'm going to write B is equals to V1, V2. And then I'm going to write C equals to 120. So these are the lines of code that I have to plug in. And then I would say B is inverse of A times C. So which would give me the value for V1 and V2. We could do this manually as well. Okay, when I do this manually, I get expressions, I get values for V1 to be 9.09 volts and V2 to be 10.909 volts. Okay, makes sense? So let me quickly recap what I have done. The main fundamental step here. There are three basically steps in node voltage method. Node voltage method. The first step is to identify a ground node. The second step is to identify different nodes and set up node voltages. And the third step is to look at currents flowing out of each of that node. Questions, please. Let's do one more example.
So during an exam, then we could come up with our system of equations, and if we have MATLAB on our laptop, we're allowed to just plug it into MATLAB and go with those answers, even on exams.
Yes, yes,
Okay.
yes. You're able to do that. There are calculators as well that can solve equations for you. So you're welcome to use them as well.
All righty, thank you.
Yep.
Hey,
So let's do
Professor,
one more. Yes.
can you explain? Sometimes on the homework, I get confused when they ask, for instance, they would ask the power at the current source 2A. And I saw some examples online were using, I think, this way of using the node voltage source.
Okay. So the idea is you want to look at the current. That is, here I have defined all the currents to be leaving in a particular node, at a particular node, and I apply KCL at that node. So when it comes to calculating the power, all you have to do is you have to find the voltage at that current source and multiply that with the current, V times I.
Okay, so is there, because when I look at that current source, I never think of there being a voltage at that point. But so there is a voltage around that current source, the 2A?
There is, if you think about it, the value that I said I got for V2, 10.909, that shows up here. Okay? That's 10.909 volts over there. And remember the other side, that's ground, that's 0. Okay, so there is a voltage around this current source, 10.909 to 0. So that guy times I, that's the power. That's the power that the current source is consuming.
Okay, thank you. That makes more sense. I was just treating it like a regular current, but I guess it's different because it's a current source, right?
Regular current source. The only thing about current source is that the current through them is set 2 amperes. Okay, the voltage between them, that does not matter. Okay, that can be set by the rest of the circuit. Okay, even if this is 10 volts or even if this is 3 volts, that does not matter. The current is constant. But for sure, there is some voltage around that current source.
Okay, thank you.
Yeah. Other questions, please.
Professor,
So what?
I just have one question for your KCL for voltage 2.
Okay.
You know how you have the direction pointing towards V2, right, for that node?
You're talking about the one shown in purple, right?
Yes, yes. So
Yes.
isn't it typically when the current is going towards the node becomes negative, and when the current is leaving the node, the current is positive, right?
Sure.
When you do a KCL for your second node, you got V2 minus V1. Why would it be positive V2? Why isn't it negative V2 and plus positive V1?
Well, they're exactly the same. The idea is realizing that, let's say, so I put it x plus y equals to minus z is one way of writing it. X
Okay.
plus y plus z equals to 0 is another way of writing it. I'll show you what I mean. Okay. Your idea is that, let's say, let's stick to the idea that the current is going along the blue line from V1 to V2. Okay.
Yes.
Then what would I do if I'm doing KCL at node 2, right?
Yes.
When I'm doing KCL at node 2, I'm going to erase this part and I'm going to take this off. Okay, so what I'm going to say is the current entering the node. What is the current entering the node?
2 ohms. I mean, yeah.
V1 minus V2 over 2 ohms,
Yes.
right? that is exactly equals to the sum of currents leaving the node, which will be V2 over 10 ohms plus V2 or
Yeah, that's how I would get the answer. Yeah, 2 amps. And then would you just
right?
move it to the other side, making the V positive? Oh, that's what you did. I'm sorry. I didn't see that. You moved it to the other side, making it equal 0. That's how you
That
get
that they're
positive.
equivalent. They're exactly equivalent.
Yeah, they're
You each
equivalent
got,
that way.
yeah.
Okay, I'm
So
sorry about that, but thank you.
no. I think that's a very good question that clarifies the point that it does not matter as long as I um, add all the currents leaving a node to 0. That
Yeah.
is exactly same as defining one of the currents to be flowing in and putting them on opposite sides of the equation. So this guy is on this side. You see the equivalence now, and it's important to make that connection.
Yeah,
I'm glad
it's
you
all
asked
right.
this question.
Yeah, I got it. It's my bad. It's just I've been reading the book a lot, and I'm starting to miss a bunch of steps.
No, this is good. I'm glad you asked this question. Okay, so let's. So the idea is when you solve this set of the equations, we get the answer to be V1 to be 9, V2 to be 10.9. So in other words, we got a value for V1 to be 9.09 volts and this guy to be 10.909 volts. Now we are able to calculate all the different branch currents. Does that make sense? Okay, so we will move on with node voltage method, another example. Okay, we'll do another example for node voltage method. Let's see. This time we are going to use dependent current sources, something like this. Interesting. Okay, so I'm going to solve this circuit using node voltage method. Copy that. So let me add a page here. Okay, node voltage method with dependent current sources. Okay, okay. Example 2 for node voltage method. Okay, let's look at the node voltage method. The first step again is to identify the ground node. Well, there it is. I'm going to term this guy as the ground node. Okay, I'm going to name this guy as the ground node. That's step 1. Step 2 is to identify the different nodes. I'll call this node 1. Okay, and I'll call this node 2. Okay, that's this guy is node 1. This guy is node 2. Now the next step is to define the node voltages V1 and V2. Okay, that's node voltages V1 and V2. Let's follow. The only thing that is different about this problem is that there is a dependent. Okay, there's a dependent voltage source. The voltage of this guy is dependent on the current through this branch. Okay, let's see how we can solve this problem. Okay, the first step is to set up KCL at node 1. Okay, so when I'm looking at node 1, I look at all the currents that's leaving the node and sum them to 0. Okay, let's look at all the nodes that are, I'll call this I1, call this I2. This is anyways given to be I5. Okay, so the idea is I1 plus I2 plus I5 is exactly same as 0. Okay, that is KCL at node 1. So what is the value of I1? I1 is V1 minus 20 volts by 2 ohms plus I2 is V1, that's the current flowing down, minus ground by 20 ohms, plus I5, this guy, current flowing right through the 5 ohm resistance, is V1 minus V2 over 5 ohms, and all of that will sum to 0. So this is my equation 1. Okay. The next step is to set up KCL at node 2. Okay, KCL at node 2. So the idea is I'm going to define terms like this. I'm going to call this. There are 3 currents flowing out of this node. So I'm talking about the node right there, node 2. Okay, so I'm going to call this I4. I'm going to call this I5. And this is, I know, negative I5. Okay, because that's exactly the opposite of current I5. Okay, so let me set up KCL at node 2, which implies I5 plus I4 plus the opposite of I5. All of that should equal 0. Okay, now what is the voltage here? The voltage there, if you think about it, is 8 times I5. That is because of the voltage source, this guy, which puts a positive voltage of 8 times I5 over there. Okay, so when it comes to dependent current sources, I have to do an extra step of expressing the equations in terms of I5. So let me continue this KCL at node 2. The first step, I5, is the current flowing down, which is V2. So let me go back to my V2 minus 0 over 10 ohms, plus I4 is the current going to the right. So if you think about it, it is V2 minus the voltage at that node, which is 8 times I5, 8 times I5 over 2 ohms, plus negative of I5 is the current going to the left, as shown by the purple arrow there. All of that should sum to 0. This is my equation number 2. Okay. Now what I can do is, now if you think about it, there seems to be another independent equation. There seems to be another term, I5. What is the value of I5? Okay. I5 is the current going from node 1 to node 2. That is I5, right? That's the current. So that can be expressed as V1 minus V2 over 5 ohms. Okay, I5 is V1 minus V2 over 5 ohms. Okay, so this is equation number 3. This is the constraint equation. This is the equation that represents the independent variable. As you can see, how many unknowns do I have here? There is V1 and there is V2. Okay, these are the unknowns. There is V1, there is V2. Okay, and then I5, even though it appears to be an unknown, it really is not, because that can be expressed in terms of V1 and V2. It's not an independent unknown. I5, even though it shows up in the equation a bunch of different times, I can plug the value of I5. I can plug not the value, the expression V2 minus V1 or V1 minus V2 over 5 ohms in place of this guy and eliminate I5 as the unknown variable and express all my equations in terms of V1 and V2. Then I can solve the system of linear equations to get an expression to get a value for V1 to be 16 volts, V2 to be 10 volts, and then I5 to be 1.2 amperes. Does that make sense?
So from where we stopped, we're just solving the system of equations for the unknowns.
Correct.
Okay.
Correct.
Yes, then yes, it makes sense.
And then there is some more hints on how to proceed. The equations that you eventually get appear like this. There is one equation in terms of I5. There's another equation, and there's a third equation. You can plug them into MATLAB, and you can get the value for V1, V2, and I5. Okay, so that's the idea of node voltage method.
So that third equation then, that's the equation for I5?
That's the equation for, let's see. That's this guy shown in green.
Okay, perfect. I was just double checking.
Yep. Okay, so 5I5 is V1 minus V2. And you can rearrange this guy. 5I5 equals to V1 minus V2. So they're identical equations. Okay. Other questions, please. So here is the general procedure. To review again, the idea is to start with a ground node. The first step is to start with a ground node. Then I identify two nodes. Then set up KCL at node 1, KCL at node 2. Then it's a matter of solving a system of linear equations. Okay. The only thing that we want to remember is when there is an independent current source, or there is a dependent, when there's a dependent variable, V5, I5, or something like that, that leads us to a third equation to resolve that dependence. Okay, so all the information that we need can be set up from two node voltage equations. So this is called the node voltage method. Two equations coming from the KCL at the different nodes, and then the constraint equation. The third equation right here is not coming from nodes. Well, it's coming from nodes, but it's the constraint equation. Okay. All right. So that's the idea of node voltage method. So let's look at the third. Let's look at the other method, the mesh current method. Okay. Let's quickly go back and see what we did so far. We started this chapter, techniques of circuit analysis, by defining certain terminology. A node is a point where circuit elements join. A reference node is the node assumed to be at the lowest potential of the ground. Then I defined a loop. We know what a loop is. Any path in a circuit that begins and ends at the same node. And then a mesh is a loop that does not include any other loops. That's the section 4.1. Okay. Then we went on to the idea of node voltage method, which I illustrated a bunch of different times here using the general approach. Okay. Then on to mesh current method. Okay. And then we talked about node voltage method with dependent current sources. Okay. Dependent current sources with an example. Let's talk about mesh current method. So this is another way to create necessary equations to solve a circuit. Okay, it is based on the idea of KVL. It's a variation fundamentally of KVL. Earlier we saw that node voltage method. It's nothing but a play on KCL. Okay, mesh current method is nothing but a play on KVL. Is a manifestation, it's a different manifestation of KVL. Okay, so this is a variation of KVL where equations are voltages around a mesh. Okay, and we define what a mesh is. We start by defining mesh current for each loop. The equations are usually written in terms of currents and other circuit values. Earlier, the equations are written in terms of voltages. Remember, node voltage 1, so on and so forth. Okay, so circuit values typically resistances, impedances. Okay, let's take a look. Let's take a look at how we do the node mesh current method. Okay, let's start by doing this. Okay, capturing this guy. Okay, copy this. Okay, let me see, add a page here. Okay, here is the circuit that I'm trying to solve using mesh current method. Okay, mesh current method. Okay, the idea is I'm going to start by identifying 3 mesh. Okay, 3 meshes. First one is right, so okay, the first one is that guy. Okay, then there is another mesh, this guy. Okay, and then there's a third one. Let's see, it's this guy. Okay, corresponding to this, I'm going to set up 3 currents. So pay attention, this guy, I'm going to call it as I1. I'm going to call this guy as I2, and I'm going to call this guy as I3. Okay, so there are 3 meshes that I identified, and corresponding to those, I'm going to identify 3 currents in each of these meshes. Okay, the first thing I'm going to do is to start by writing KVL around mesh 1. Okay, which is like I mentioned, this guy. Okay, that's mesh 1. So as always, I begin at the lower left corner and follow a clockwise path. Okay, when I follow a clockwise path, let's pay attention to the voltage drop, beginning with the negative 40 volts in the independent voltage source over there, followed by, I'm following in this direction, and then the resistance is also shown like so. So there is a voltage drop of I1 times 2 ohms, right? I1 times 2 ohms. Then let's follow through to this resistance, okay? In this resistance, if you think about it, let's pay careful attention. There are 2 different currents flowing in this. There is a current I1 or IA flowing from top to bottom. That's I1. And there's also a current I2 flowing from bottom to top. Okay, so let's do that. Let's see how we can set up the equation based on that. So when it comes to the voltage drop across 8 ohms resistance, it's going to be a sum of I1 times 8 ohms So remember, I'm still following this path. Okay. Then this resistance is also shared with the second mesh. So I have to account for that as well by writing a 8 ohms multiplied by negative I2. All of that will equal 0. Okay, so in other words, I can write this equation to be voltage drop across this guy, okay, which is negative 40 volts times the voltage plus the voltage drop across this guy, in which there's only one current I1, and the voltage drop across the resistance, 8 ohms resistance, that guy. Okay, so maybe it's easier if I write it this way. Okay, let me rewrite this equation just to for illustrative purposes. The first is negative 40 volts plus, then there is a current of I1 flowing through the 2 ohm resistance plus the voltage drop across 8 ohms resistance is 8 ohms times the current flowing in this. All of that equals to 0. So there are two ways to look at it. The idea is when it comes to this resistance here, 8 ohms resistance, there are two currents flowing in two opposite directions. Okay, that's what I have to account for. So let's do the exact same thing. KVL around mesh 2. KVL around mesh 2. Okay, so that's about the second mesh here, which is this guy. Okay, now as always, I begin at the lower left corner and follow a clockwise path along that mesh. Okay, let me see if I can set up my equations for that. Okay, the equation for that is going to, there are two branches of current flowing through 8 ohms resistance. So the first resistance from lower left that I encounter is the 8 ohm resistance. So when I'm following the clockwise pattern, this current I1 appears to be opposite to that direction. So negative I1 times 8 ohms plus there is one current I2 that is flowing in the clockwise direction, that is aligned with my direction. So this is I2 times 8 ohms, okay, plus there is a voltage drop from here to here because I'm following a clockwise pattern. So there is that guy, okay, 6 volts, 6 ohms times I2 plus, how about this resistance here, okay, there's a current of I2 flowing along my clockwise direction, 6 ohms, and then there's a current of I3 flowing opposite to that direction. All of that equals 0. Okay, so when it comes to this resistance over here, and I'm following my clockwise path, I see I2 is along this clockwise path, and I3 is opposite to that. Okay, so three equations, two of which I have already set up. Okay, yes, now this is equation number 2, this is equation number 1, and then let's write the third equation as well. KCL, KVL around mesh 3. Okay, KVL around mesh 3. So KVL around mesh 3 is again, I start at the lower left corner. So let's see, that's the mesh 3 here. Okay, I start at the lower left corner. I'm talking about this mesh over here. I'm adding up the voltage drop in the clockwise direction. Okay, when I'm following the clockwise direction, pay attention, I3, I defined it to be in the clockwise direction, and that seems to be aligned with the clockwise direction I am following. So I3 times 6 ohms. But don't forget this guy. There is this current flowing in from top to bottom, counterclockwise direction for this circuit. So negative I2 times 6 ohms. That's the current, that's the voltage dropped in the 6 ohm resistance. Then I come to this 4 ohms resistance plus I3 times 4 ohms. Then I'm following along the clockwise direction through this guy, which is a plus 20 volts equals to 0. So that's the third equation for me. Okay, so there are 3 equations that I set up using 3 mesh. The first mesh is shown by the I1 current here. The second mesh has an I2 current, and the third mesh has an I3 current. Does that make sense? Questions, please.
So basically, for independent sources, when the source is leaving as a negative, it becomes a positive, and when it's leaving as a positive, it'll become a negative, right?
Yes. And when you compare these two things, I have written, the idea is the path that I follow. You see what I mean? So you have to follow the direction of the current. When you're going from top to bottom, the current is going that way, and then you encounter a plus followed by a negative, then you deem it to be plus, passive sign convention. And the other example, when you're going from negative to positive, as in here, then you account for the negative sign over there. That's the negative 40 volts. Does that make sense?
Yes. Thank you.
Yep. Other questions, please.
So then the final step is just solve for the unknowns, correct? And figure out what our currents are for each mesh?
That is correct. There are 3 equations here. Let me write those equations out here for you. So the equations, when you simplify them, they're going to take this form. IA is 10 ohms plus ID times negative 8 ohms plus IC. I call them I1, I2, and I3, right? So I'm going to stick with that. I1 times this guy, I2 times this guy, I3 times 0 ohms equals to 40 volts is the first equation. The second equation is I1 times negative 8 ohms plus I2 times 20 ohms, okay, plus I3 times negative 6 ohms equals to 0. That's my second equation. And then the third equation is I1 times 0 ohms plus I2 times negative 6 ohms plus I3 times 10 ohms equals to negative 20 volts. Okay, that's my third equation.
Then just to be sure, you find that it's just algebraic manipulation, correct? I'm not missing any formula or anything? Okay, perfect.
That is correct. It's just algebraic manipulation. Okay. Other questions, please. So it's easy to see that here. So there is, let's see, I1 plus times 2 plus, let's see, there is an I1 plus 8 ohms. So that gives you I1 plus 10 ohms. Then there is a, let's see, negative I2 times 8 ohms. So that's negative I2 times 8 ohms. And there is no I3, that's 0, which gives you negative 40. Take it to the other side, it's positive 40. So it's just algebraic manipulation. Okay, so let's do one more example. Let's do one more example for, and then the rest is easy to solve. Plug that into MATLAB. You get expressions for you get values for I1 to be 5.6. Let me write that out here. I1.
So in MATLAB, then we would just add one extra variable to our matrix and solve in a similar way.
Correct.
Okay.
Correct. So your matrix is going to be 10 and negative 8, 0, negative 8, 20, negative 6, 0, negative 6, 10. And then there's a third variable. So you're doing a 3 by 3 times 3 by 1 equals to 1 by 3. Okay, something like that. Not 3 by 1. Okay, so the lines of code, that's still going to be 3. You just plug in the value for A, you plug in the value for C, and then you write B is inverse of A times C, and then it will throw out the values for I1, I2, and I3. Okay, so when you do that, the values that you should see are I1 equals to 5.6 amperes, I2 equals to 2 amperes, and I3 equals to negative 0.8 amperes. Okay, so that's the idea of mesh current method. Okay, mesh current method. So here is the equation that you set up for MATLAB. That's your A, this is your B, and this is your C. Okay, so here is your code for MATLAB. So A is written to be one line, B is that guy, and C is A over B. Okay, and then you get the value for C. All right, so that's the idea of mesh current method. We'll stop here. When we come back in the next class tomorrow, I'll do some more example problems for node voltage and mesh current method. We'll do 2 examples of node voltage and mesh current method, starting with this guy in the next class. Questions, please. Questions so far.
None
Let's
here,
see.
sir.
Sorry, go ahead. Say that again.
I just said none here, sir. Thank you.
Okay, perfect. So we are pretty well. We are going on schedule. As a matter of fact, as you can see, we are a little ahead of the schedule. Okay, so so we have time to work on example problems, take a break here and there. If you have questions, you're welcome to email those questions to me. I may be able to take a look at some of those problems in the class, so on and so forth. Okay, so we are not only on schedule, we are well ahead. So good job. I'll see you folks tomorrow then.
If we run into problems with our homework, would you like us to email you the questions, or do you have office hours that we would come to?
I prefer email. I don't have summer office hours. So to the best I can, I try to find some time to reply to your email. So I feel free to email me your questions.
Okay, and maybe we ask questions for homework in class time like today, or would that take up from lecture too much?
You can do that. You can do, if you have questions, you can ask them in the class as well.
Okay, perfect. Thank you.